Good morning, everyone. We are greeting from Czech Republic and welcome after a long time on our IDEA StatiCa webinar. This webinar will be focused on reinforced concrete structures designed via CSFM. It's a new method, compatible stress field method, like a shortcut. Let me introduce the presenting. Myself, I'm Lucas, and my colleague Petra.
Good morning, everybody.
We are both product engineers and have been working for a couple of years in IDEA StatiCa. We are mainly focusing on the concrete part. So when you join to the session, the control panel will appear on the right side of your screen. Use the control panel for typing the questions, and we will try to answer your questions during the webinar, and the more sophisticated one will be answered after the webinar to your email. So some words to content. At first, we will focus on the design of the concrete structures, some intro, some practical example, the theory behind CSFM, result interpretation, and mainly the comparison between the strat-and-tie analysis or strat-and-tie model and new method CSFM. So I will pass a word and presenter to my colleague Petra, and Petty, it's up to you. So switch off the camera. Start again.
Sorry, I was muted. Hello again. So our topic is reinforced concrete design. Most of engineers check their structures on the level of cross-section, which is 1D, or on the level of point, which is 2D. We can imagine under this 1D or 2D concrete design, beams and slabs. These analyses and checks are based on several assumptions. One of the assumptions is Bernoulli-Navier hypothesis, which assumed that the cross sections remain plane and perpendicular to the axis. This assumption can be applied into so-called B regions. They are depicted by yellow color in this slide on this picture. But as you can see, the structure composed of B and D regions, and there are many of them. So, and unfortunately, we cannot apply this assumption into these D regions. So, what do structural engineers do in practice? They have several options. They can use specialized software limited to specific D region. For example, we can have a simple software for designing the corbels or frame joints or other detail. These softwares are simple and they are good, but once you have a complicated detail, non-standard task, you cannot use this software. Then you can, of course, have some other, it doesn't have to be a software, it can be an Excel sheet. And the most famous or most common method is strat-and-tie method, which is, again, a good method, but there are some limitations, and we will talk about it later. So if the engineer encounter complicated non-standard detail, he or she must take different software, more sophisticated scientific software like ANSYS or Midasphere and many more. The problem is that these softwares are very robust, and the user need to be advanced and need to understand a lot in this software or to this software, and it's very time consuming to input the all parameters and all things related to complicated model which are also which were developed in order to simulate the reality. So do we have another option? Do we have a better option? The answer is yes, we do. There is a new method, compatible stress field method, CSFM, implemented in IDEA StatiCa Detail. This method enables engineers to design effectively, safely, and economically the suitable dimensions of concrete member, layout, and amount of reinforcement. From the physics point of view, it is actually implementation of modified compression field model, and the analysis is based on the, finite elements. There are separate finite elements of concrete and reinforcement. Two other aspects are codes and trust. Material characteristics are based on the codes, both Eurocode and ACI. So the engineer can use this method and still be under the code on the safe side. And why should we trust this new method? The answer is that the method is verified and validated at the University ETH Zurich. So we can trust this method. What are the suitable concrete members and details for this method? So by CSFM, we can solve any topology, as you can see on these two slides, and we are not limited anything, any topology, any load, and it is also suitable for several civil engineering industry. So it doesn't matter if you are interested in reinforced concrete only, or pre-stressed concrete, or bridge designing. So we are leaving the introduction part and enter the practical part. I have chosen a very well-known example. It's a deep beam with large opening, and together we will model this example, talk about the tools how to design the reinforcement, and eventually we will check the whole structure. Why did I choose such a example? This example is very well known, mainly because of the strut and tie method, and I'm sure that some of you have met this example when they were studying this or learning this method. So I'm gonna skip switch to IDEA StatiCa and open IDEA StatiCa Detail. I have prepared it. I have completely empty project, so I'm going to create a new one. So I click New, set the material parameters and concrete cover. And I'm not going to use templates, but I will use this general input because I've made some drawings, and I use these drawings to import the geometry and reinforcement. So I'm going to use import from DXF. I will choose the file, click on the edge, outline, and second click to opening. And this is the whole process of creating the geometry. We have two entities, wall and opening. We have to set the thickness of the wall, so it will be 400 millimeters. Then we will use other entities. So I clicked on this button and I will choose point bearing plate. We will model two supports. The first one will be fixed support, and I will just modify the dimensions. So half meter wide bearing plate and 1.1 thick. Then I need to set the right distance. So now it is perfect. I will simply copy this support and place it here at the right bottom edge. So I will just change this functionality measured from the end, and it will be sliding support. So I'm gonna uncheck this X direction. So I have supports. The structure is now supported. And the last thing which will be added is load transfer device. It will be bearing plate. Again, I will set the dimensions, and it will be on the edge number 1. So I will change this edge and I will shift it more to the left, and it will be 2.5 meters. So now it's according to the reference example. So I will look at the visualization of this model. So here we can see our wall thickness and the opening. Then we can jump to load, definition of the loads. Here it will be very easy. There will be just one concentrated force acting on this bearing place. We will add another load case and 3 combination. First, let's define the load cases. The first is the load case which represents a permanent load. So I will choose point load and write the value. It's minus 690 kilonewtons. Then I switch to LC2, choose the same load, concentrated force, and just change the value 1370. Then I go back to load cases and combinations. Load case is permanent. Load case number 2 is not permanent but variable. Then I click to combination, go to edit combination, and set the load factors, partial factors. So the first factor is 1.35 and 1.5 for variable. The second combination will be for SLS check. So let's set characteristic here. The factors are equal to 1. And the third combination will be quasi-permanent for assessing cracks and deflections. And here one will be for LC1 and LC2 will be 0.3. So this is the setting or a partial factor setting for our combination. To speed up the calculation, we usually uncheck load cases and focus only on the check of the combinations. So we have a factor load just according to the reference example. Now we have loads and we can move to definition of reinforcement. So in the navigator, I go to reinforcement. Before we design the reinforcement, I would like to introduce our design tools. Let's start with linear analysis. So I just performed a linear analysis. The output of this analysis is a layout of tension and compression in the structure with respect to acting load. So imagine there is this force and we have a compression and tension in the structure. If you prefer lines, you can switch to lines and, for example, use scale 20 to see properly how the principal stresses look like. Also, we can use these filters and check the compressions on some level, some value. Then we have another tool, topology optimization, which is different analysis based on energetic principle. This algorithm is looking for the optimal volume of the structure in order to transfer the load through the structure. So then we deal with so-called effective volume, as you can see. And the output of this analysis are, let's say, Stressstrain models, which represents, again, main or principal stresses, principal tension and compression. Both these tools can be used for the design of the reinforcement. So if an engineer deals with complicated detail and doesn't have a clue where to place the reinforcement, he or she can use these designing tools to place the reinforcement in the surroundings of the main tensions. So this is the effective volume, 20% of the whole structure, and this is how could the Stressstrain model look like if we have only 20% of this structure, 20% of the volume of the structure. If I click and choose to 40%, we get thicker lines and a little bit different or similar model. So now it's the time for designing the reinforcement. So I click on Input Edit button. I can leave the outputs from topology optimization or linear analysis on the background and follow the main ties in order to design the proper reinforcement layout. Again, similarly as in geometry definition, I will use import from DXF, and also I will add the reinforcement in the software. So I recommend to use this functionality where the layout of the reinforcement or the shape of the reinforcement is more complicated. So I will import these two inclined reinforcing bars. They represent the main tie in the structure. Maybe for these purposes, I will turn off the topology optimization to see or to show the reinforcement. So I've imported these two curves into IDEA StatiCa detail. And right now, I just need to define the number of layers, check the diameter and number of bars in one layer. So this will be set to 2 and 2. And the diameter was read from the or loaded from DXF because I did the drawing by means of curve and set the global thickness of the curve, and it was set to 22 millimeters, and this program can see this and automatically input this value here, so you don't have to take care about it. So we have this reinforcement, and I just need to define one more thing, and this would be special anchorage at this end of the reinforcement. And maybe there should be one. So at this, oh no, here should be one, and here should be two. Yes. So at this end, I will define standard band. As you can see, we have a band here, special anchorage type. Then I click to GB2, which is this tie, and again, I will set the 2 bars in a layer and the same anchorage at the end. For better imagination, we can click to Real 3D and check if the model looks okay. So now it's correct. Then we can proceed with other group of bars. I'm not gonna design all the reinforcement definition because it takes time and we do not have time for this. So I will show just how to insert another group of bars, and then we switch to complete model. So let's switch to model 2D view. We have another group of bars, and now we need to first define the position of this group of bars. So we will model reinforcement, which is horizontal in this direction according to or in the surrounding of this opening. So let's switch the definition from polyline to outline. Then we will define the master member. This will be this wall, V1. Sorry. Yeah, I will insert another group of bars, and it will be, yes, this is the right settings. So we don't use polyline anymore, but the shape will be defined by according to the edge. So master member is V1, edge is also 1, and now we modify the position on edge. We will use this edge from the end, and we know that it is 2030 from the beginning, and it ends at dimension 2470. So now we have the length of the reinforcing bar. We will use this normal or standard anchorage, and we don't want to place the reinforcement by means of concrete cover, so we won't use settings. If you remember, we have defined concrete cover at the beginning of the project. It was 30 millimeters, but we want to place this reinforcing bar to this position. So we will set user defined cover. And now we have it in the correct position. Only we need to define the number of layers. So it will be 5 layers. The distance will be 300 millimeters. Change the diameter 13 millimeters, and the number of bars and layers is equal to 2. So if I click to a real 3D view, I can check if I define it correctly, and yes, it is correctly. And we would proceed in the same manner with other orthogonal reinforcement, but we don't have time for that. So let me skip to a different project which is already reinforced. So here you can see the reinforcement in the surrounding of the opening, the main tie at the bottom, and inclined one. I switch to model 2D view, and this is the reinforcement which correspond to reference example. So we have modeled, loaded, and reinforced the concrete member, and we can perform the analysis. But before that, we will go to materials and models and change the concrete strength in compression. Again, we do this because of the comparison of the reference example and this model. And in the reference example, there is design concrete strength 17, if I remember correctly, yes, 17 megapascal. So we need to change this characteristic strength, which is then equal to 25.5 megapascal. Here you can see stress-strain diagram of the concrete, but we will talk about the stress-strain diagrams later. So now we have everything set, and we can go to check and run the analysis. I will use this time to talk about the method behind CSFM. So let me switch to presentation and start explaining. So the theory behind CSFM's compatible stress field method. From physical point of view, it is a compression field model with ties. The CSFM assumes fictitious rotating stress-free cracks that open without slip, and consider the equilibrium at the cracks together with the average strains of the reinforcement. So we have a crack, and due to the equilibrium, we can calculate average strains. The model considers maximum concrete and reinforcement stresses. So we have reinforcement stresses and concrete stresses. While we neglecting concrete in tension, except for tension stiffening effect. Sorry. So the tension stiffening effect is depicted on the picture D. As you can see, Stressturn diagram of the reinforcement, and the blue curve represent tension stiffening. Then we have another aspect, compression softening, which is depicted here, which is automatically calculated based on biaxial stress state. I will talk about the stress strain diagrams in a few minutes. And last but not least, the behavior between reinforcing bar and concrete is described via shear stress slip relationship, the last picture, this rigid plastic relationship. As it was mentioned at the beginning of this webinar, the analysis is based on finite element method. Here you can see the analytical model. The model consists of finite elements of concrete, 2D elements, which are interconnected via multi-point constraints, these blue-green lines, and special bond elements, this purple one, to reinforcing bar. At the ends of the reinforcing bar, there are springs which simulate the anchorage. So if you remember, we have defined special anchorage in form of bend, and this is the in analytic point of view, this is the spring. So as I promised, I would like to talk about talk more about stress strain diagrams. So when we deal with concrete, we need to distinguish between ULS and SLS checks. So if the concrete is in ultimate limit state, we calculate with parabolic stress strain diagram or bilinear diagram. It depends on the user which he or she want to use. By default, we calculate with parabolic stress strain diagram. And the user input is this blue curve. It is this code-dependent curve, which represents material, but the software calculates with this red one, which is influenced by compression softening, which is automatically calculated based on these relations. This Kc factor is the factor which reduces concrete strength in compression. Then we check serviceability limit states, but we use different stress strain diagrams. We use this blue and red curve. It depends if we calculate stresses due to short-term or long-term effects of loads. And it is linear or bilinear diagram. Then we go to or proceed to stress strain diagrams for reinforcement. Again, the user can choose between bilinear diagram with increasing branch, or this second one with plastic branch. By default, CSFM calculates with this Stressstrain diagram, and we don't distinguish between ULS and SLS checks. We have the just one diagram, but again, there is tension stiffening effect considered, and the user input is the blue line, the one which is codependent, but the software can calculate or consider the tension stiffening effect, which is the result of rebar embedded in concrete and the actual help of concrete between the cracks, that it is a contribution of the concrete in tension. So that would be all about the theory behind. And now we get to CSFM results. So for this, I will switch to the software. So the analysis was performed. We have the results. And as first, the user see so-called summary results, where we can see immediately if the concrete member satisfied the code checks or not. We distinguish ULS and SLS checks. Immediately we can see the governing checks. So in this example, in this task, it is a strength of reinforcement which is the limiting factor. We can switch between ULS and SLS check, but this is just a summary, and it's better to go to these steps to look at the more detailed results. So the first, or second tab, strength. Here you can see the strength check of the concrete and separately the reinforcement. So let's start with the concrete. Here we see the actual check. If we want to see the stresses, we switch in the ribbon here to sigma C, and we can see the stresses in this structure. I can switch off the reinforcement and study the distribution of the stresses. I can also draw the mesh of the finite elements and look like more in more detail. So this is stress. We can also look at the strain of the concrete, but I would like to highlight Kc, which is the factor which reduce the strength, compression strength of concrete, and this is the compression softening effect, which is applied here in the surrounding of the main strut, because there is a huge compression in this direction, but the transfer in the transverse direction there are tensions, and this is captured by this Kc factor. So this is the compression softening effect. If I want to check out the results of the reinforcement, I need to click to reinforcement, and again I can look at the strain or stress check, or if I'm more interested in actual stresses, I go to sigma S and look at the actual value of the reinforcing bar. I can click to different row and look at the actual entity. which is selected. So this is the ULS state and ULS check, and then we can check anchorage. So anchorage is checked on the reinforcing. Here we check the stress at the surrounding of the reinforcing bar, and check it with the stresses which is allowed, which are bond stresses, allowed bond stresses. So we have the results are in terms of stresses or forces, or we can just check the actual anchorage forces or stresses. Then we switch to a stress tab. This is a check which is related to serviceability limit state. That's why we can distinguish between long-term effect and short-term effects. This is just a check. If I click to sigma, I can see the stresses in serviceability limit states, and also check the effects of the loading. So right now I click on short-term effects. If I click to long-term effects, the stresses are a little bit lower. This is related to concrete. If I want to check reinforcement values, reinforcement results, again, I go to reinforcement and choose the reinforcing bar which I'm interested in. Then we have a crack check, which is like the highlight of this SLS check, because the user can see the cracking, which is extremely beneficial, and you can see the place which is with the highest crack width. You can see how the cracks could look like, and also we can display the distance between the cracks. And the last check is the deflection. So I click on this deform shaped, and this is how this structure will be deformed under the concentrated force. We can distinguish between short-term deflections, long-term deflections, and you can also display the total deflection. This auxiliary tab is the tab for users which are interested in these results more deeply, and let's say there are some inter results from the solver. So if I go back to summary, in the summary you can see everything, all the checks, and this is just the detailed results. So we went through the results, and right now we enter the part of comparison, CSFM and strat and tie method. So this example, this deep beam with large opening, was extracted from literature from Professor Schleich. He solved this example by means of 3 strat and ties models, and then he added them together. Now we get to the actual comparison between these two methods. I have extracted the results from IDEA StatiCa detail and read the value of the stresses at the supporting areas A and B, and under the concentrated load. And I compare these values to the values provided by STM in the literature of Professor Schleich. And we can see that the values are very similar or basically the same. Of course, I didn't take the concentrated values. I read the values in the larger area of the from the CSFM results. So we can say that for the ULS, we get to quite good comparing. And as a second, I studied the ultimate load provided by CSFM. So what do you think? Do you think that we get a higher or the same load, which is defined in Stressstrain time model? So let's look at it. So the reference load is 3000 kilonewtons. This is the load which is defined at the reference example. So I took or I loaded our CSFM model by load of 4500 kilonewtons and ran the analysis. Maybe I didn't mention that the analysis in IDEA StatiCa detail in CSFM is non-linear, and the loads are or the structure is loaded in increments. So I overloaded this concrete member, and the analysis stopped at some level. So for the first row, it's 68%, then 83 and 88. And then I calculated the actual load which was transferred through this structure. So the first example or the first model was modeled exactly the same like in the literature, but I didn't use any special anchorage at the bottom area, I mean here. So we got this ultimate load, which is equal to 3065 kilonewtons, which is let's say almost the same like the reference load. But even in this example, there is written that it is considered or assumed that in this area, in this zone B, the ties, the horizontal and also the inclined ones, will be with special anchorage at these ends with some hooks or bends. So we should compare the CSFM model with this special anchorage, with the standard bend, to be or to preserve the same assignment, the same task. So I did this. I shown this during the modeling that we used the bends, and the ultimate load is 3,749 kilonewtons. So we got 25% higher load than in STM. Then I did another research and tried to model perfect bond, and we got obviously higher, but the value is not so far away like in this example, in this case. And one important fact at the end, the governing check at the first example was anchorage at the bottom zone. So if there is a special anchorage defined, then the limiting factor is reinforcement strength. So we can say that it is extremely important to model the concrete model as a whole. It means use concrete elements, reinforcement elements, and do not forget about anchorage types. So let me summarize the whole practical part and a comparison between these two methods, between CSFM and STM. So thanks to CSFM, engineers can design their structures effectively, safely, and economically. We cannot say that a strat and time method is effective because it's very time consuming, and as it was shown, maybe it's not as economic as CSFM. Another important aspect is that CSFM provides unique solution. Most of you know that there are several strat and time models which are correct, and we don't know exactly which one is the most correct one. So this is the comparison, this summary. And of course, everybody needs to check their structures, and it is extremely important to check according to ULS, according to provide ULS check, but also SLS check, because in these days we design thinner or lighter structures with large opening, with non-standard topologies, and we don't know exactly where the cracks will be. So that's why it is important to check also according to serviceability limit state. So that would be all from the practical part. Lucas, has anybody asked a question?
Yes, we've got many questions, so I select only two of them, and the other ones will be answered after the webinar to your emails. So I think the interesting one is Betty, how can we find out the reactions due to the assigned loads? Can you show it in the application? It's better for visualization of.
Okay. Yes, I will show it. It's better to show it. So I hope you can see my screen. So we have our structural model results, and by default, we are in the stress flow representation, but we can click on this reaction and loads, and this is how we can check the reactions. Right now it is for extreme combination. I can also click for current and select, for example, C1. This is the ULS combination, 3000 kilonewtons, and those are the reactions. So it's quite simple how to check it. Anything else?
Yes,
Or do we
super. It's a great answer. Yeah, the second one, Betty, can you show us where we can define or how we can define the self weight of the structure of the wall? How to put it?
Sure. So we need to go to the loads. So far, the self weight of the structure is not calculated automatically, but user has to define it. So let's define the self weight of this member. So I click on load case LC1, go to load impulses, add another entity, and I will choose surface load. Surface load, and here you should define the value which corresponds to surface load of the self-weight. So let's say it's minus 10 kilonewton per meter squared, and maybe I will change the scale of the load, and you can see how it is applied.
Yes, super. I think it's a brilliant answer. So I think
Thank you.
that time is up. So I will take a presenter.
Okay, so thank you for the attention.
Yeah, thank you, Petty, for a brilliant presentation. Uh, So I hope you will see my screen and some information just briefly. The after webinar, please dedicate some time to a short survey and assign the classification to our speaker Petya. The 5 is the best one, and the 1 is let's say the worst one. So we have also some additional questions. If everybody, from all of you, is using for checking, co-checking, and designing our application IDEA StatiCa Detail and our method CSFM, or if not, please enter what kind of methods are you using for code checking of these type of the structures, or what's your approach? Yeah, and we are thank you for it. The recording will be uploaded on the YouTube till tomorrow, or will be in the section webinars on our resource center. So I hope, or I'm thinking that we have a lot of freshmen on our webinar, so you can download or apply for a trial on our webpage. You can see it in the bottom part of this slide. There is a free trial, so you can fill in the form and you receive immediately the trial version. And of course, we have in our resource center on the webpage ideastatica.com a lot of published tutorials, verifications, and many more to CSFM method, and to two more things like for connections or concrete also. So you can looking forward also to the next webinars, because we are going to release a new version of IDEA StatiCa, IDEA StatiCa version 20, and the webinar will be on 27th May 2020, and it will be focused on the steel and concrete news in the version 20. So you can looking forward on, let's say, partially loaded area. And for people which are focusing on the connections, or for you also, on the 17th June will be recorded, or will be connection Wednesdays, where will Jana and our duo Jana and Adam. So I think that's all from our sides. Thank you for your attention, and we will looking forward for next webinar. Yes, so see you soon, and bye bye.
Have a nice day. Bye.